Small consumer electronics have been getting smaller and smaller, but the amount of heat they give off has been getting greater. Here to tell us about a new material that could lower these overheating problems is the museum's Corrine Tate. Hi, Corrine.
Hi, Susan.
Well, anyone who spends a lot of time with a computer on their lap knows that they can get pretty warm. Why is that, though?
Well, there are a lot of parts inside electronic equipment that produce heat. And because electronics are such a big part of our lives, everybody has experience with this. Touching electronics that are running, they do generate heat. Some of the parts of electronics that produce the most heat are actually the computer chips inside them. On computer chips, usually made of silicon, there are millions of transistors, these tiny electrical switches. And that's a lot of electricity running through a very small space, turning off and on very, very quickly. And the friction of all those electrons flowing through that space and the resistance in the wiring is what's generating a tremendous amount of heat. And as we make electronics smaller and more powerful, we're just putting more power through more transistors in an even smaller space, and it's just exacerbating these heat problems.
And one solution cannot be to actually remove these transistors because that's the whole point of having the computer. So we need to find another way to keep a computer cool. But why is it important to keep it cool? Why not let it run hot?
Well, a material like silicon actually doesn't perform the way it's supposed to perform when it does heat up. And the way that we've traditionally kept electronics cool is to run a fan. And if you open up a computer, you'd notice that there are fans running there and there's heat sinks and things to try to dissipate the heat. But as we make these electronics smaller and smaller, actually having a fan is becoming less feasible. So that's why scientists are starting to look at new materials. Since silicon really has a problem when it does heat up and it doesn't perform the way it's supposed to perform, maybe we can find some other materials that can better handle that heat issue.
And you're here to tell us about a possible new material that scientists think can be used in that respect.
Yes, I am. So this new material is called graphene.
Is graphene anything like graphite, I would assume?
You're absolutely right. Graphene and graphite are related. Graphite, which is a naturally occurring mineral that we find in nature, it's the soft gray material inside pencils. Graphite is just a huge stack of carbon sheets. And each one of these carbon sheets is kind of a honeycomb lattice of these hexagon-shaped carbon rings. And if we're able to separate out one single sheet of carbon, that's exactly what graphene is.
So lots and lots of graphene piled on top of each other is graphite.
Exactly. And carbon is something that's very common, and there are so many different forms of carbon. Coal, diamonds, graphite, fullerenes, carbon nanotubes. All of these are made entirely of carbon. The only difference is the way the carbon atoms are bonded to one another and the atomic structure that they have. We knew that graphene could theoretically exist, one of these single sheets, because we understood what graphite was made of. But scientists really didn't think a single sheet would be stable on its own. They thought if you got a single atomic sheet that it would scroll or buckle or bend, that it wouldn't really retain its flat, planar properties.
Have scientists been able to isolate then a flat sheet of graphene, or have they only been able to suppose it exists from graphite?
Well, up until 2004, it was just theoretical, but, as recently as 6 years ago, they hadn't done it. And then in 2004, a man by the name of Andrew Geim, who works at the University of Manchester in the UK, was able to isolate a single sheet. And it's kind of funny, they used very primitive tools to do it through a process they call mechanical exfoliation, but really it's just peeling little crystals of graphene off of a big chunk of graphite using Scotch tape. And using the Scotch tape, they just peeled off incrementally thinner and thinner flakes until they had isolated a single sheet, just one atom thick. Now, this was a tiny, tiny flake, but they were able to isolate it and even measure some of its properties, and that's when research in graphene just really exploded.
But that seems like a really difficult process, that every time you want graphene, you have to take a chunk of graphite and get little and little pieces off. So since 2004, have they improved the method of being able to get these sheets of graphene?
They have, but it actually took a while. They've only really improved the production methods in the last year or so, because It really was a very laborious process that yielded only these tiny flakes. And obviously, if graphene is going to be used for all these wonderful applications that they think it can be used for, they needed to find a way to scale it up. So there's been a lot of work into trying to figure out how could we make these big, useful sheets of high quality graphene. And there's been quite a bit of research recently into trying to grow graphene on wafers of silicon carbide. And what they do is they end up heating it up a tremendous amount, getting rid of the atoms they don't want, so they're left with just a single flat monolayer of carbon. And that's how they've been growing it, one layer of this crystal sheet at a time.
So now you have these silicon-based surfaces, and you have just one layer of graphene that's growing on top of it.
Well, the graphene is grown one layer at a time, but it's easiest to come up with a few layers together at a time. It's still hard to isolate just one single layer on its own. So they end up with a few layers together. And what's been really exciting recently is that Professor Alexander Ballandin at UC Riverside did a lot of research on these layers together, where you just have a few layers together, and found out that actually even when you have a couple of layers bunched together, it still behaves as a single sheet of graphene. So it retains all these great properties, and it's much easier to produce a few layers of graphene stacked on top of one another than just one single sheet on its own.
And it still seems to behave in the same way, better than silicon, but the same as a single sheet of graphene.
Yes, and graphene does have some incredible properties. It's really strong. Its breaking strength is something like 200 times that of steel, and it has really incredible electrical conductivity and heat conductivity. And because of these really unique properties, a lot of scientists and a lot of people in industry as well knew that this would be really useful for electronics and could potentially replace silicon computer chips in the future.
Because if it's good at electrical conductivity, it can be used very well in these transistors, and if it has good thermal conductivity, then hopefully it won't get quite as hot as the silicon will. So it should kind of solve both those problems.
Exactly. It manages the heat problems much, much better, but does have these unique electrical properties to be used in computer chips.
You talked about a lot of really cool properties that this graphene has. It sounds like they might be useful not only for computer chips, but for other things as well, now that they're over this kind of manufacturing issue of being able to get these single or very small layers of graphene. Are there any other applications that scientists already have in mind for it?
Definitely. I mentioned that it's very strong, and also because we're talking about just these few sheets, it's actually totally transparent as well. And that makes it perfect for other new innovations, touchscreen technologies and LCD screens and flexible bendable electronics, even organic photovoltaics. So there's a whole host of applications that scientists are really excited about exploring now that we're able to better mass produce these sheets of graphene, and that we know that even a few sheets works just as well as a single one.
Yeah, that seems to be one of the biggest parts of all this, is not just being able to mass produce it, but knowing that you can have these multiple layers and it's going to work just as well as a single layer.
Definitely. Getting over the fabrication issue is the biggest problem in scaling up these new technologies.
Well, I look forward to hearing about more of these graphene applications now that that production hurdle has more or less been overcome. So thanks, Cretan, for telling us all about this use in small consumer electronics.
Thank you so much, Susan.
That's it for this week's show. Be sure to come back next time for more of the latest in science and technology. This podcast is a production of Current Science and Technology at the Museum of Science in Boston, part of the Boston community for over 175 years. For more information, visit our website at www.mos.org/cst or email us at podcast@mos.org. Thanks for listening.